In the last class, we had derived the equations for projectile motion and seen all the various relations for motion in 2 dimensions. Let us today try to we will solve some problems in kinematics, and let me start with the recap of projectile motion. As we recall, projectile motion is motion of a particle which has been released with a velocity v0 at an angle theta 0, and when we look at this particle, this is released in air. It has, as we see, because this velocity is inclined, and if we draw our x and y coordinates like this, initial velocity has got both x and y components. So, therefore, this is a motion in 2 dimension. And as we saw, the way to tackle this type of problem is to separate out the motions in horizontal and vertical directions. So, here if we look at the motion in horizontal direction, then in the horizontal direction, the acceleration of the particle, which I write as ax, is 0. The initial velocity, which I write as vx0, this will be equal to v0 cos theta 0. And if we look at the vertical motion, which is in a sense decoupled from the horizontal motion, then here if we look at it, the acceleration is equal to the acceleration due to gravity, and because y is pointing upwards, ay is equal to minus g. And if we look at the initial velocity in the y direction, this will be equal to v0 sin theta 0. So, now from this we derived, and if we look at it, we get 2 straightforward relations. So, we write the further equations for Vx and Vy and the displacement along x and y, and as before we split the horizontal and the vertical components separately. So, at any time t later, Vx will be given by V0 cos theta 0, and then we have a term plus At. So, it is plus Ax times t, but because Ax is 0, so therefore, the Vx in the x direction will be, the x component of velocity will be constant. The vertical component of velocity, we can write Vy is equal to Vy0 times Vy0, let us write it, Vy is equal to V0 sin theta 0 minus g times t, because g is equal to the acceleration in the y direction. So, then if we write the distance travelled in the x direction, so let us just make this small picture again. We start from a coordinate of 0 0, and then the projectile travels a path. We want to find out at any location x comma y what are the coordinates. So, therefore, the x coordinate will be given by x 0, which is 0, plus v 0 cos theta 0 t, and the y coordinate will be given by v 0 sin theta 0 t minus half g t square. And from these 2 equations, we got the equation of the path by writing y as a function of x, and this we got by eliminating time. And if we do that, then what we see is t is equal to x by v 0 cos theta 0, and this is the equation for t, and then we put this in the expression for y. So, we will get y is equal to v 0 sin theta 0 times x by v 0 cos theta 0 minus half g times x upon v 0 cos theta 0 square, and this gives us the expression. When we simplify this, we will get y is equal to x times tangent theta 0 minus half g upon V0 square cos square theta 0 times x square, which we explained last time was the equation of a parabola. So, now once we have this equation, then one of the things we look for in the projectile motion is the distance which the projectile travels before it hits the same level or ground again, if it has been thrown from the ground. So, let us say the coordinates of this point will be x is equal to r, y is equal to 0, the initial point is 0 comma 0. So, it is very clear to get the expression for r for this range, all we have to do is put y is equal to 0 here, and that will give us the value of x. And we have seen this. Also what we do is, if we want to calculate the time of flight of the projectile, if we call that as t, then this time, this will be the time. For this we will need to go to the velocity equations. In the velocity equation we have x Vy is equal to this. If we look at the x expression for y is equal to V0 sin theta 0 t minus half gt square. We put y is equal to 0 here. So, when we put y is equal to 0 here, we will get 0 is equal to V0 sin theta 0 t minus half gt square, and from here we will get the expression for the time of the flight, which will be equal to 2 V0 sin theta 0 upon g, and then we can, once we know the time, we can get the range as V0 cos theta 0 into t. So, this becomes equal to V0 cos theta 0 into 2 V0 sin theta 0 upon g, and this we can write it as 2 V0 square cos theta 0 sin theta 0 upon g, and this can also be simplified upon g. So, these are some of the things which we can get. Now, let us look at this expression again, and that this is, let us see the expression. This is the projectile path. The y coordinate which is travelled is given by V0 sin theta 0 t minus half gt square. So, now what we realize is that this particle, when it travels in a projectile motion, it crosses the same y value at 2 times t1 and t2. And if we look at this equation, then it is very clear that for the same value of y we get a quadratic equation in t, and the roots of this quadratic equation, there are 2 roots, they give the value of t1 and t2. Now, in some of the problems, if we need to find out this time, that is delta t, which is equal to, if we need the expression for delta t which is t2 minus t1, then we have these 2 roots t1 and t2, and we can get the, if we solve for the 2 roots, we can subtract them and get the expression for t2 minus t1, and that will give us the time which the particle takes to travel the distance, which is when it crosses the same height at 2 different locations. Now, here when we work this out, sometimes because this is a quadratic equation, in a quadratic equation we know sum of roots is equal to minus b by a, and the product of roots is equal to c by a, where the equation is given by ax square plus bx plus c is equal to 0. So, if we want to find out t2 minus t1, then actually what we are looking at is the difference of the 2 roots. So, if we have sum of roots, let us say the 2 roots of this equation are alpha and beta, then if I look at alpha plus beta whole square, minus 4 times alpha beta, this will give me alpha minus beta whole square. So, therefore, if I need alpha minus beta, then what I need to do is I need to take the sum of roots, square them, minus 4 times the product of roots. So, therefore, in a case like this, if I need to find this delta t, I need not solve for the two roots. I can express this expression in the form of ax square plus bx plus c is equal to 0, and then from here I can get the difference of two roots, because alpha plus beta will be given by minus of b by a, alpha beta will be given by c by a. So, these things I can feed in here, and from there I can get the difference of roots. So, this I will leave it to you to work out in terms of the parameters of our problem. I have told you the basic method how this can be done, because in certain problems you may be asked this time, or there may be a problem where you may be asked to find delta T1 and delta T2, where delta T2 would be the time for another height, and maybe this height difference would be given to you, and then you can express this difference of heights in terms of these variables. So, a problem like this could be easily made and worked out, and you can try this out on your own. So, now let us also see some other things in the projectile motion. The maximum height, this we showed in the last class also, is attained for maximum h is equal to maximum in a projectile motion when Vy is equal to 0. So, therefore, when you put Vy is equal to 0, the time turns out to be equal to V0 sin theta 0 upon g, and you will realize this is half the time which it takes to complete its motions to reach the same level, and this should be expected because the time a particle takes to go up is the same time it takes to come down in 1D motion, and the vertical 1D motion in a projectile is decoupled from the horizontal motion. So, therefore, when we work out that height, the height if we want to work out now, time is V0 sin theta 0 upon g. So, now we put the expression in the formula for y. So, it becomes equal to V0 sin theta 0 into time, which is V0 sin theta 0 upon g, minus half times g times t square. So, V0 sin square theta 0 upon g square, and when we work this out, so this y is equal to h, and this turns out to be equal to V0 sin square theta 0 upon 2g. So, this is the maximum height which maximum height attained by the projectile, and the time taken to attain this is equal to t by 2, where t is the total time for the flight. So, what we have is the total time taken, we have seen this is equal to 2 V0 sin theta 0 upon g, and the maximum height reached is V0 square sin square theta 0 upon g. Now, from here if we look at t square becomes equal to 4 V0 square sin square theta 0 upon g square, and this we can see will turn out to be equal to 8h upon g. And also if we work out the expression for h in terms of range, what we will get is h is equal to r the range times tangent of theta 0 upon 4. This again I will ask you to work out. You will have the formula for range, you have worked this out, and this also turns out to be equal to t square g divided by 8. So, some of these things based on what we have done, I would expect you to work them. Now, let us also look at the trajectory formula for y in terms of the range. And for that we look at the expression for y. Y is equal to x tan theta 0 minus half g x square upon v 0 square cos square theta 0, and so this we can rewrite, this will be equal to x times tangent theta 0 minus g by 2 v 0 square. Now we have cos square theta 0, so we multiply by sin theta 0 and divide by sin theta 0. So this will become equal to x times tangent theta 0 minus, then we will have, if we look at it, there is a 2 v 0 square cos theta 0 sin theta 0, that is equal to range. So that becomes equal to minus g sin theta 0 upon r times cos theta 0. So this becomes equal to x tangent theta 0 minus g by r tangent theta 0. So let us now express the vertical distance travelled by the projectile in terms of the range, because sometimes this could be useful in looking at some of the problems. So let us write y is given by x times tangent theta 0 minus half g x square upon v 0 square cos square theta 0. So this we can write it as x tan theta 0 minus half g x square v 0 square cos theta 0 and we multiply and divide by sin theta 0. So this becomes equal to x times tangent theta 0, and then in the second term what we get is there is a 2, there is a v 0 square, there is a cos theta 0, there is a sin theta 0. This product becomes equal to range. So therefore we get minus g times x square upon r, and then we have tangent theta 0. So this expression then can be in fact simplified further. We can write it as x times tangent theta 0 into 1 minus x by r, and one can probably write this x times tangent theta 0 into r minus x upon r. So this way one can express. So these are, what we are doing is we are interplaying between various variables. We have r, we have h, we have t, and depending on what we need we can express the other variables in terms of this. So for example, let us solve a problem. What is given is that a projectile is released with a velocity v 0 angle theta 0 as we have specified, and during its path of motion at any position x comma y, the angle which the projectile makes with the origin with the starting point is alpha, and if this is the end point r, if I join this with a straight line, this angle is beta. And what we have to find is a relation between alpha, beta and theta 0. So therefore, to have a look at this problem, let us say at this height is given by y. The coordinates are x comma y. So this height is given by y. So tangent of alpha is given by, let us call this distance, this is x. So tangent of alpha is given by y by x. Tangent of beta is given by y divided by r minus x, that is tangent of beta. If we add the two, we will get tangent alpha plus tangent beta is equal to y by x plus y divided by r minus x, and when we work this out, so this becomes equal to y times, so this is tangent of alpha plus tangent of beta, this is equal to y times r minus x plus y times x divided by x times r minus x. So, this will be equal to y times r divided by x times r minus x. And if we look at the general expression for y, what we had got just now was y is equal to x times tangent theta 0 times r minus x by r. So, therefore, y times r by r minus x times x, this is equal to tangent of theta 0. So, this will imply tangent alpha plus tangent beta is equal to tangent of theta 0. So, therefore, a problem like this can be easily solved. What you have to see in these problems is that which are the given variables and in terms of which expression you can find them. And in case if you do not need to remember any formulas, all you need to remember is the expression in terms of x and y. In x coordinate, in x direction acceleration is 0, therefore, Vx is always V0 cos theta 0, and the distance travelled will be V0 cos theta 0 into t. In y direction, the acceleration is equal to minus g. So, therefore, the vertical velocity will always be equal to V0 sin theta 0 minus of gt, and the distance travelled in the y direction, assuming y to be positive, will be equal to V0 sin theta 0 t minus half gt square. Now, there is one more thing one can see in projectile motion, and what we have is, let us look at the formula for the range. Tells us range is equal to V0 square sin of 2 theta 0 by g. So, now if we are given the value of V0 and theta 0, that means there is one particular velocity and theta 0, and if we look at another projectile which is thrown with the same initial speed V0, but at an angle of pi by 2 minus theta 0. When we look at these two projectiles, that means one projectile is thrown at an angle of theta 0, another is thrown at an angle of 90 minus theta 0. Now, if you calculate the range for this will turn out to be equal to r1 will be equal to V0 square sin square 2 theta 0 upon g, and r2 will be equal to V0 square sin square of 2 times pi by 2 minus 2 theta 0, and this will be nothing but sine of this angle is pi minus 2 theta 0, which is the same. So, this will be equal to r1, because sine of pi minus theta is equal to sine of theta. So, therefore, for a given initial velocity, the same range will be covered by two angles, and the sum of these two initial angles will be equal to 90 degrees. And also clearly from this we can see for a given V0, the range will be maximum when theta 0 is equal to pi by 4 or 45 degrees. So, a body with angle which is thrown with an angle of at an angle of 45 degrees covers the maximum range. But notice, while we talk of ranges here, which is the distance, it does not mean that the time t1 and time t2 taken by the two will be the same. The times will be different, and that is obvious from the fact that this time of flight depends on the initial vertical velocity. And when theta zeros are different, the initial vertical velocity of projectile 1 and projectile 2 will be different, even though the ranges may be same. And similarly, the heights, the maximum height which they clear or which they reach H1 and H2 will also be different. So, the range will be the same, but these things will be different, and sometimes you may be asked to find the relations between T1 and T2 or H1 and H2, and these things you can do by playing around things here. Now, as a last this thing on projectile motion, let us take a case of projectile on an inclined plane. Actually, the equations we have derived earlier are valid here also. But when we talk of an inclined plane, maybe as we will see, let us look at the problem. So, suppose we have a plane here, a plane, this is at an angle alpha, and we throw this is the coordinate 0 0, and we throw a projectile with a velocity v 0 at an angle theta 0 from the horizontal. So, theta 0 is the angle which the projectile makes with respect to the horizontal, and this is the incline along which the projectile is thrown. Now, this will go up and it hits and it comes back and hits here. So, now let us say this was the origin, let this be the point B, and let us call this distance now as the range. Now, notice this range is different from the earlier problem in the sense that in the other cases where we the previous cases we had done, the point when it was hitting back on the ground was at the same level. Now, the projectile is hitting at a different y level as compared to the starting point. So, now if we want to find this range in terms of these parameters which are given to us. So, now which are the parameters? We have v 0, the starting velocity of the projectile, theta 0, the angle from ground, and we have the third thing alpha, which is the angle of the inclination, and we want to find the range. Now, when doing this, it may be easier because now if I choose, so for this particular problem, I choose if this is the incline and this is the perpendicular direction, I choose x along the incline and y perpendicular to the incline, and this is how the projectile is going. So, now if I look at this, we start from origin 0 0, and the final point which I want to find, the coordinates of that will be r comma 0, because now y is perpendicular to the incline and x is along the incline. So, now when we look at this, the projectile is experiencing an acceleration which is equal to g. Now, this direction, the vertical direction, is not parallel or perpendicular to x and y. So, what we do is we resolve the acceleration along x and y directions. So, if we choose x and y as I have chosen, then what will happen is so now what we see is this direction, if I look at the perpendicular direction, this is the direction parallel to the plane, this angle is alpha, this angle is 90 minus alpha. So, the component here, if this is g, then the component in this direction, this will be g cos alpha, and the component in this direction will be g sin alpha. Actually, it is g cosine 90 minus alpha, which I can write as g sin alpha. So, therefore, when I look at the acceleration now, the x component of the acceleration is equal to minus g sin alpha. I have taken x along this direction, g is along the minus of this, and the y component of acceleration, as I have chosen this x and y, will be equal to minus g cos alpha. So, we have to realize these 2 points. So, now the difference when I use this formulation of x and y which are inclined as compared to the previous case, then what I get is there is an acceleration in the x direction and there is an acceleration in the y direction. Whereas, previously the acceleration was only along y direction, and this difference is coming because of the way we have chosen our axis. So, if that is, we write it like this. So, now all we have to do is, let us look at, so Ax is equal to minus g sin alpha and Ay is equal to minus g cos alpha. Vx0 is equal to, now we have to look at the x component of the velocity. So, velocity is v0, makes an angle. Now, this v0, the velocity, is making an angle of theta 0 minus alpha with the x axis and with the perpendicular component. So, therefore, what we have is Vx0 will be equal to v0 cosine of theta 0 minus alpha, and Vy0 will be equal to v0 sine of theta 0 minus alpha. So, once we have this, then we can just move along. We write our equations for Vx, Vy, x and y. So, what we have is Vx is equal to v0 cosine of theta 0 minus alpha minus g sin alpha t, and for Vy we will get Vy is equal to v0 sine of theta 0 minus alpha minus g cos alpha t, and then if we write for the x component will be equal to v0 cosine of theta 0 minus alpha t minus half g sin alpha times t square, and from here what we will get is y is equal to v0 sine of theta 0 minus alpha t minus g cos alpha t square by 2. So, in the vertical component g is replaced by g cos alpha, and in the horizontal component we get this extra terms because of g sin alpha. So, now when we get this expression for y, now at r comma 0 y is equal to 0. So, this will imply for this value 0 is equal to v0 sine of theta 0 minus alpha times t minus g cos alpha t square by 2, and from here we can get the value of t. So, we get t is equal to 2 v0 sine of theta 0 minus alpha by g cos alpha. So, this is the time which the projectile takes to come to the comes back on the plane. Now, we have to find the expression for range. Now, one way of doing this is we can plug this value of t in the expression for x, which was x is equal to v0 cosine of theta 0 minus alpha t minus half g sin alpha t square, and that will give us the value of r. But we can also look at this in another way, and that will be slightly simple numerically. So, let us draw this picture again. This was x, this was y, this is we are looking at range, this angle was alpha. Now, what I say is, let me call the horizontal direction as x star. Then what we have is the distance which the projectile travels in when it goes a distance r, let the horizontal distance travelled be r sub h. So, now if I want to find this, in r sub h is the horizontal distance travelled, and this was nothing but v0 cosine theta 0 into t. Because if I look in terms of x star coordinates, I still have the old equation, the x distance travelled is nothing but initial velocity multiplied by time, and the time taken for the when it comes to its position B, which was given as r comma 0, will be the same time capital T, and capital T, which we have just now seen here, is equal to 2 V 0 sin theta 0 alpha upon g cos alpha. So, therefore, I can get R sub h is equal to V 0 cos theta 0 multiplied by 2 V 0 sin theta 0 minus alpha divided by g cos alpha. So, this way I can get the value of R sub h, and what we realize is R sub h is nothing but equal to the range cosine alpha. It is clearly obvious from this figure, R cos alpha is equal to R sub h. So, therefore, what I get is the range R cos alpha, this is equal to V 0 cos theta 0 into 2 V 0 sin of theta 0 minus alpha divided by g cos alpha, and this gives me an expression for R, which will be equal to, if I simplify, 2 V 0 square cosine theta 0 sin of theta 0 minus alpha divided by g cos square alpha. So, therefore, I can find this, and I would have got the same expression if I would have plugged in the value of t in the expression for x and then used trigonometry to simplify the expression. I would have got the same value of R, but here I used this expression and used the horizontal component of range and its relation with R using trigonometry. I got the same relation, possibly in a slightly lesser time or whatever. So, therefore, when you have a problem where you have a different situation than what you have seen, you should improvise. For example, in this particular problem, we chose x and y along the incline, so that the expression for R became quite simple. It just became y coordinate became 0. But when we did that, we realized we had to split up the acceleration along the new x and y directions. Similarly, for example, you may have a problem where something is thrown on the incline, down the incline. I looked at the problem from up the incline, and I am not going to solve this problem for you, but what you can do is, if you choose your x like this, you choose your y like this. Now, when you resolve your gravity component, then this component, the x component, will be positive. It will not be negative, because your x is now going down. So, depending on your problem, whether x is up or down, you will have to resolve the particular value of acceleration along x and y and then solve them. Be careful about the signs. If you take y as up, then there are certain negative signs, certain positive signs. Take into account all of those signs before you complete your problem. We have seen in detail various concepts related to projectile motion. Let us look at another problem which uses the concept of relative velocity, and sometimes these type of problems are also referred to as pursuit problems. Here what is given to us is that there is an aircraft whose initial location, if one says this is B, this distance is A. So, if I look at it in terms of x, y, the aircraft initially is at A comma B, and a missile is launched towards the aircraft. Now, what is given to us is that the speed of the missile Vm is constant, and the aircraft has a speed Va, which is also given to be constant, and the missile is always guided towards the aircraft. So, given the initial position of the aircraft and the missile, and given that the aircraft is travelling and the aircraft travels along a straight line. So, Va is constant, and we can also say that the velocity of the aircraft, we can reduce this, this will be equal to VAI. It is also given that the missile velocity is constant, speed is constant, and it is always guided towards the aircraft. That means, when the aircraft goes to the next location, the missile will appropriately change its direction, so that it is always in going towards the aircraft. And here what we want to find is, we want to find the time taken by the missile to hit the aircraft. So, in problem like this, let us first draw two pictures. This is the initial picture where we have the aircraft is at this location, missile is here, and this is travelling with VA. The missile velocity is guided toward the aircraft. So, this is Vm, this distance is A, this distance is B. So, this is the configuration at t is equal to 0. Now, let us look at the same configuration at a later time t. At a later time t, the aircraft would have moved to some location other than where it started from. So, other than from A comma B, the aircraft would have come to its location, which will now be given by x, and since it is travelling in a straight line, it will, the y coordinate will always be B. And the missile now is somewhere here, we do not know the exact position, this is at some general time t, but the velocity of the missile is guided like this, it is towards the aircraft. So, here what we do is, we place coordinate system on the aircraft, we look at things with respect to the aircraft. So, now if we look at this direction, let us say this angle at any general instant between the line of the aircraft and the missile, I call this angle as phi. So, let us draw this in a bigger way. This is the aircraft, this is the missile at a general location, I draw this is this, I call this angle as phi. So, therefore, what we find is the rate of separation of aircraft and missile, this rate of separation will be equal to, that means if I am calling this as r, then the magnitude of dr by dt, this will be equal to the velocity of the missile minus velocity of the aircraft in the r direction. So, therefore, what we will have is the separation, the rate of change of this separation, this will be equal to velocity of the missile minus velocity of the aircraft in the r direction. And therefore, from here what we also see from the figure here, and in fact, here I should have not put the vector sign. So, I am cutting them now here, and if we look at this figure, what we find is the velocity of the aircraft in the r direction, this angle is also phi. So, this will be equal to VA cos phi. So, the rate of change of separation becomes equal to Vm minus Va cos phi, and if I integrate this, then what I get is dr is equal to integral of Vm minus Va cos phi dt from 0 to t, where capital T is the time when missile hits the aircraft. And this dr, when I integrate this total is equal to the separation between these two, because this dr, when we look at this is nothing but the total separation which was there, and this separation is square root of a square plus b square. So, therefore, what we get is, we get one equation which tells us square root of a square plus b square. This was the separation which was initially there, and finally the separation becomes equal to 0. So, therefore, when we integrate dr, what we will get is square root of a square plus b square. This will be equal to integral from 0 to t Vm minus Va cos phi dt. Now, here what we realize is the angle phi is changing with time. So, finding integral of cos phi dt is not straightforward, because at each position angle phi is changing. So, what we can get from here is root of a square plus b square is equal to Vm times t minus Va times integral of cos phi dt 0 to t. So, then we ask the question, can we find integral cos phi from some other information which we have in the problem? And what we realize is, if we look at the x direction, then, and because we have placed our coordinate systems on the reference frame of the plane, so the relative velocity of the missile with respect to aircraft in the x direction, this will be equal to Vm cos phi, this is the x component of the velocity of the missile, minus the x component of the velocity of the aircraft, which is equal to Va. So, therefore, what we have is, we can write this dx by dt, which is the separation in the x distance in the aircraft frame of reference, this is equal to Vm cos phi minus Va. And if I integrate this, what I will get is integral dx will become equal to integral Vm cos phi dt minus Vat, and this x distance which is moved in the reference frame of the aircraft is nothing but the initial separation, because that is the distance which the missile has to cover in the reference frame of the aircraft in the x direction. So, therefore, from here what we get is, we get the second equation, which gives us A is equal to Vm times integral cos phi dt from 0 to t minus Vat. I can call this as equation number 2, and the equation I had got earlier, I can call this as equation number 1. From 1 we can get the value of integral cos phi dt from 0 to t, and we substitute in 2, and when we do all the maths, then finally by this substitution what we will get is t comes out to be equal to A times Va plus Vm times square root of A square plus B square divided by Vm square minus Va square. Now, let us look at another aspects of kinematics, and let us look at this quantity V dot A, and let us see if we can get something from this scalar. As we see, V is the velocity vector and A is the acceleration vector. Please note that all the formulas which we have been using, like V is equal to initial velocity plus At, or the displacement is equal to V0t plus half At square, these formulas are valid only when acceleration is constant. If acceleration is varying, then these formulas are not valid. Now, we are looking at this dot product of two vector quantities V and A, and both V and A are general. That means they are not constant, they could be varying with time, and they could be in any direction. Now, what we know is, when we talk of one dimensional motion, in 1D motion V and A are along the same direction, and what I mean is they could be opposite to each other or they could be along the same direction. The angle between the v vector and the a vector is either 0 or pi. But in 2D motion, we could have v and a such that angle between v and a at any general instant, this will not be equal to 0 or pi, it can be anything between 0 and pi. And such a body in general will be moving along a curved path. Just to recap, what we had seen was when a body moves along a curved path, then the velocity is always tangent to the path and the acceleration has two components. A component which is tangent to the path, which is nothing but the rate of change of speed, and a second component which is perpendicular to the path and which is pointing, the second component points to the center of curvature of the path, which means because this is a curved path, locally we will assume if this body is moving like this, that if this is moving in this way, that if it is moving in a circle, then a second component of acceleration will point towards the center of that circle, and this is what we can call as the normal component, and this is given by speed square divided by the radius of curvature. So, this is what will always happen when a body travels in a curved path. Now, what I wanted to discuss was, if we look at this expression of v dotted with a. Now, looks like a very mathematical quantity, there is some velocity, there is some acceleration. But let us look at this, we can write this as v dotted with dv by dt, because acceleration is dv by dt, and this we can write it as d by dt of v dotted with v divided by 2. And so, this will be equal to half times d by dt of v square, where v now is without the vector, therefore, this is equal to speed. So, now from here what we can see is, if we look at this quantity v dot a, if this is equal to 0, then what this means is, if v dot a is equal to 0, that means d by dt of v square is 0. So, the physical meaning of that is that speed is not changing with time. So, speed is not changing with t, and if always, if at all times v dot a is 0, so let us write this, if for all times v dot a is 0, this will imply that the speed with which the particle is moving is constant. So, if the acceleration is perpendicular to the velocity, then the particle has to travel with a constant speed. Also, we can have a look at this sign, if v dot a is greater than 0. Now, physically when will this happen? If this is the velocity vector, if this is the acceleration vector, v dot a will be greater than 0 if this angle theta between v and a this is, if the angle theta is between zero and 90 degrees, because it is V A cosine theta. If the angle theta is between V and A is between 90 degrees and 180 degrees, then V dot A will be equal to magnitude of V times magnitude of A times cosine of the angle. So, that will be equal to, this will be less than 0. So, now as we have seen, V dotted with A is equal to the rate of change or half the rate of change of square of speed. So, if V dot A is positive, this implies d by dt of speed square is positive, and this will mean that the speed is increasing. And if V dot A is less than 0, this will imply that during the path of the particle, the speed of the particle will decrease. So, sometimes when we have to make some conclusions about quantities, we can use these mathematical facts to make some conclusions about qualitative interpretations using mathematics is what we can very easily do. So, now what we have done so far is that we have studied the equation of motions for one dimensional motion, for two dimensional motion. We did them for the case of constant acceleration. We also derived the case when the acceleration is not constant, then you write the position vector, velocity and acceleration as derivatives, that is acceleration is the derivative of velocity, and position vector, the derivative of position vector gives us the velocity vector. So, and we have seen how to differentiate the vector quantities in detail. So, we have therefore, we have completed the study of motion of a particle, of how to explain the motion of a particle. This is what we call as kinematics. So far, and also one more thing which I expressed to you very clearly is that when we look at r dr by dt, we went up to the second derivative, that is up to acceleration. Sometimes the question is asked, why do not we go to the third derivative or the fourth derivative? And the reason for that will become clear when we study what causes motion. So far, we have just studied the details of the motion without trying to understand what is causing the motion. Now, that is what is going to follow. Next, what we are going to do is, we will try to understand why a body starts to move. And what we will see is that there is a quantity called force, and when force is applied on a body, that is what causes the motion of a body to change. And this is what will be covered under Newton's law, and that is what we call as kinetics, and together kinetics and kinematics are referred to as dynamics. So, now having studied the motion and kinematics of a particle, now we will focus in our next module on the dynamics of a particle. That means, we will look at a particle and then we will relate the force to the rate of change of momentum of a particle, which we will define, and that is what Newton's laws tell us about. Newton's second law particularly tells us about this, which we will cover in the next class. Thanks.